Hello, everyone. Welcome to today's exciting webinar. I'm Tim Stark and your host for today's webinar, which is part of an ongoing series of emerging topics in geosynthetics. Today's webinar is sponsored by the Fabricated Geomembrane Institute, which is an industry-based organization at the University of Illinois at Urbana-Champaign that promotes the use of fabricated geomembranes and other geosynthetics for a variety of applications through its research, education, and technology transfer activities. Factory fabricated geomembranes and geosynthetics reduce field seaming, reduce installation time and costs, allow more modular construction, and provide consistent system quality. Today's webinar is also sponsored by the North American chapter of the International Geosynthetic Society, or IGSNA. I'm currently a vice president of the IGSNA and pleased that the IGSNA is also supporting our free webinar series. IGSNA's mission is to educate the civil engineering industry about geosynthetics via webinars, educate the educator courses, student and professional memberships, and conducting geosynthetic related conferences and workshops. During today's webinar, we welcome questions and comments which can be typed into the question box in your control panel. You may send in your questions at any time during the presentation, and Professor Bartlett and I will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be automatically sent to all who attend the entire webinar, so you don't need to email for the PDH certificate. Okay, today's webinar speaker is Professor Stephen F. Bartlett of the University of Utah, who is giving his webinar from Incheon, Korea, where Steve is helping set up a campus for the University of Utah. In his spare time, Steve is a leading expert on the use of geofoam, especially for transportation projects. Steve was intimately involved in the significant use of geofoam for the improvements made to Interstate 15 around Salt Lake City for the 2002 Winter Olympics, as well as other locations. His various degrees are from Brigham Young University, where he conducted still pioneering research on earthquake-induced soil liquefaction. It is great that Steve squeezed us into his busy schedule to give our May 2019 webinar that's titled Geofoam Applications for Roadway Infrastructure. Please welcome Professor Steve Bartlett, where it's after midnight in Incheon, Korea. So Steve, thanks for joining us.
Well, thank you, Tim, for the introduction, and greetings from Incheon and the campus here in Songdo. We are starting a new civil engineering program here, so it's kind of exciting to be a part of that. Also, in this presentation, I think I need to recognize some people that I've collaborated over the years with this. One of Tim's former students, Dave Ardiano, who is at the University of Memphis, and also Jan Vaslestad from the Norwegian Public Roads Administration. The three of us, have done a lot of work together, and some of the things that I'm going to show you are direct results of those collaboration. As Tim said, my initial involvement in geofoam happened in 1996 with the I-15 reconstruction project, and I'll show you some of the slides from that today. But obviously it was a very fast-paced project, and we benefited from the research being done not only in Norway but in Japan, and also by DeWitt Neguse from Syracuse University helped. And we, in a very large way, implemented geofoam as one of the major strategies for meeting the very rapid construction schedule. So I'll go into my slides, and then we'll certainly leave some time at the end for discussion. And I encourage you to do so and ask me, various questions, whether it be about geofoam or the integration of geomembranes to protect geofoam. So geofoam is kind of a trade name for expanded polystyrene. We sometimes call it EPS geofoam. There are other types of foams that can be used for geofoam The other type that's less common is extruded polystyrene. Expanded polystyrene by far is used, at least in civil infrastructure, than any other type of foam. Obviously, it's a lightweight cellular plastic material that is manufactured to fairly tight specifications, so it's a fairly known material with little uncertainty, at least in terms of its material behavior and properties. It's molded in blocks, as I'll show you just in a minute, and quite often we use these blocks and place them directly for embankment construction, and we do that untrimmed so that the blocks still fit relatively tightly together, and we can create various embankment configurations that I'll show later. Also, besides highway construction, you will see it used in other purposes, architectural, landscaping purposes, and I have a few slides at the end to show you some of those uses. So there is a process for heating the beads to expand them and mold them. This slide shows initially there's a pre-expansion. The beads themselves have pentane gas that's been impregnated within the bead, and as it's warmed up by steam, it expands to about 50 times its original size, and it's what's called pre-puff. That pre-puff in the second stage is sometimes air dried and prepared for a further expansion and put into a maturation bin, and then later injected in a second stage of heating into a block mold. The types of molds that we use for civil infrastructure are those that are used mainly for forming insulation, and the geofoam comes out of the block and then is later cut into slabs if you're using it for insulation. But we, again, use it mainly uncut. So on the upper left-hand side of this slide, you can see the raw styrene beads with the pentane gas that's impregnated, and then those on the right you can see have been expanded. That is the pre-puff. And then in the second phase, you can see a block coming out of the block molder. And then the block are later placed by the construction crews. The block can be of various sizes depending on the size of block molder that the particular manufacturer has. Typically, the block that we were using was about 3.5 feet by 4 feet by about 20 feet long. Those type of blocks were weighing about 220 pounds per block, so it took a crew, usually of 4 instead of 2, to place that size of block. The block that you're seeing here is about half the size of what the block we used on I-15 some years ago. So here's a block being ejected out of the molder, and it is then cured and stabilized and then later transported to the project. But we found over the years that, again, I think it's important to realize that in the plant, they can trim the block to get the dimensional size fairly precise, but in my view is generally in most civil engineering projects, particularly for routine embankments, that's not needed. But it is important to know that the block does slightly curl a little bit. Maybe over the full length of a 20-foot block, you might see an inch of curl in the block as it cools down and cures. So who started this? Well, the Norwegians, being thrifty people, realized that they had a problem. This is just near Oslo, within about 20 kilometers of Oslo, and they had a bridge approach that was constructed of earthen embankment on top of peaty soils. And with time, the peats were undergoing secondary compression and causing unacceptable amounts of bump at the bridge at this particular bridge in Flom. And so the idea was, could we come up with a better way maybe to stop this kind of consolidation settlement? The Norwegians had been working with expanded polystyrene as an idea for a insulated pavement, mainly in permafrost areas, to keep the permafrost from unthawing during the summer months. And so they thought, well, gee, we already have some experience with it, and its compressive strength seemed to be adequate for embankment. So they said, could we use it instead of just a thermolite an insulating slab underneath the asphaltic pavement, could we use it as a lightweight embankment? So the construction procedures you see here was to come in and remove some of the existing earthen embankment, unload the embankment, and then replace it with about 2 meters high of expanded polystyrene embankment. And so doing this essentially did stop the long-term secondary compression of the peats, and it worked quite well and was in place for more than 20 years. Of course, after that, there was a lot of technical exchange between the Norwegians and the Japanese. Expanded polystyrene went to Japan mainly during the mid-1980s and was used extensively by the Japanese. So the industry has benefited greatly by the research and construction done by the Japanese, and then later introduced in the United States primarily in the early 19 to mid-1990s. The predominant specification used for civil engineering is ASTM D6817. So this is the one that we call out to specify the type of foam that we want. And in this slide, you can see across the heading that is in yellow different densities of foam. EPS 12 means 12 kilograms per cubic meter, and so on and so forth as you go across the slide. The density of foam that we use primarily in roadway and highway construction is EPS 19 and sometimes EPS 22, which means 19 to 22 kilograms per cubic meter. So this type of material is approximately 1/100th the weight of compacted fill. So it is quite lightweight compared to compacted fill. The most important property on this slide is actually the compressive resistance at 1% strain. We use that as a design parameter to decide what is the combined dead load and live loads that can be held by the EPS. So generally, when you specify a nominal EPS 19, you can use this to know that the minimum compressive resistance would be 40 kPa, or in this case, 5.8 PSI. So this is probably the most important property in this table, is that compressive resistance. I want to just show a little bit of laboratory data so you get an idea of how the material behaves. As you can see initially, as you go through the stress strain curve, that in 1 to somewhere around 2% strain, you can see the materials start to yield and have some strain hardening. So the design really is, to use the 1% strain values, which is about 45% of the compressive resistance at 10% strain. So that is the most important thing, obviously, to measure on the project, is what is this stress strain behavior. In the quality assurance quality control program, there are specimens of 2-inch cubes that are tested, and the basis of that testing determines what would be the acceptance on the project. So this is routinely done both sometimes by the manufacturer within the plant and also as the specimens are delivered to the project. I should add, going back to this slide, there are some applications where we want the geofoam to yield and go into the plastic range. Those are more seismic applications, or applications where we're trying to reduce earth pressures. I'll talk a little bit about that, but for embankments, particularly for bridge approaches, and that we are not allowing the EPS to get close to the yield. And the reason for that is if we get too close to the yield point in expanded polystyrene, then it will creep with time, and those creep movements could be unacceptable. Okay, so what do we use it for? Well, obviously to reduce soil loads on soft ground. So it has a wide application in bridge approach areas. Generally, the bridges themselves are pile supported or on some type of deep foundation system, and the expanded polystyrene geofoam was then used as a lightweight embankment around the bridge approaches to reduce the amount of primary and secondary consolidation settlement. Also, because of its lightweight nature, it certainly improves the stability of side slopes and road widenings or the bearing capacity embankments built on soft compressible ground. We've also used extensively in cuts and stability of landslides. Maybe a cut slope is unstable, or you're doing a widening on an area that is unstable, and you can use it as lightweight fill to not increase the driving forces on the head of a landslide. So that is quite a common application. And then just rapid construction. If any time the construction's being held back by particularly waiting for consolidation to occur, you can bypass that whole consolidation process by using such lightweight embankment materials. So I put a slide here of the construction of I-15 in the 1960s. We had these settlement records when we were reconstructing in the late 1990s, and they were invaluable to us in telling us about the rate of primary consolidation and also some of the magnitude of the primary consolidation and a little bit about the secondary compression. So in the green on this slide, this is on a semi-log plot. So the left-hand axis is either fill height or settlement in feet, and on the right is time. And I've shown here the year it began in 1964, April, and then you see 1965, 66, 67, 68, and 69. So you're looking about 4 or 5 years of data here. But what's interesting from this is you see the final embankments heights were just short of 40 feet high, and those embankments caused about 4.5 feet of primary consolidation settlement. And you can see 2 very definite rounds of primary consolidation settlement. So these are obviously very damaging settlements. And this is primarily caused by the Lake Bonneville clays, which is the ancestral lake to the Great Salt Lake. It's a Pleistocene lake that deposited somewhat compressible clays about 15 to 20 meters thick throughout some of the central part of the Salt Lake Valley. So that's the geotechnical challenge. The other thing as you look at this slide is that the time to complete primary consolidation for these cycles that we see are approximately 2 years per each cycle. So you can see that this can be a very problematic from a schedule standpoint. If you're reconstructing an interstate that we were doing in 4 years, it was really two-year projects because we had to reconstruct one side of the interstate, switch the traffic over, and construct the other side. And so time was getting very important. And obviously we did use PV drains to accelerate the consolidation, but there's just some cases due to either the magnitude or the rate of consolidation that our traditional methods just didn't work. So expanded polystyrene lightweight embankments were introduced in some of these problematic areas. Well, I put some slides in to show you if you don't get this right, what can happen. This is south of Salt Lake City in Provo, Utah, which is about 40 miles south, and this bridge was built on compressible Lake Utah clays and also Lake Bonneville clays. This embankment was constructed to its full height. It was allowed to undergo primary consolidation, and then the bridge was built. But you can still see there is probably here on the left-hand side, you can see that the concrete covered spill slope has settled probably about 9 inches in this slide. So the embankments are continuing to settle. The pile foundations probably haven't moved too much, and this causes still a tremendous bump at the bridge. So this was later remediated by jackhammering out all the approach slab and some of the concrete pavement prior to the approach slab and had to be repaired. So it can be problematic if you don't get things right in terms of settlement. The I-15 reconstruction project, initial design was started in 1996. Construction started probably mid 1996 during the summer, and was completed fall 2001 prior to the Olympic Games. The length of the construction was about 27 miles right through the heart of Salt Lake City, widening of several lanes on both sides of the interstate to accommodate new traffic lanes and HOV lanes through the center part of the valley. The main reason for use of expanded polystyrene geofoam on the I-15 project was that of utilities. If you're either placing new fill or placing a fill in a widened area, if there's buried utilities that parallel the corridor or maybe cross the corridor in a transverse direction, the placement of new fill is going to cause primary consolidation settlement and some secondary consolidation settlement. And for many utilities, this is just too large and it would be very damaging. So this was, of the EPS that was used, I would think about 80% of this was used in areas where there were utilities that were buried. What this allowed was new fill to be placed without relocating the utilities, saving tremendous amount of cost in terms of relocation of the utilities, but also a tremendous savings in time. What I'm showing you here is 3 embankments of geofoam in a widened area. This is an approach ramp to I-15 coming from I-80. So this is I-80 westbound. And each of these embankments that you're looking at are about 200 meters long and probably about 8 meters high in terms of expanded polystyrene. And there were buried utilities all along these widened areas. So this is some pretty impressive construction. And each of these embankments that you see, the contractor was building those in probably about 3 weeks' time, where conventional construction with PV drains, placing embankments, surcharging, use of MSC walls, and that was probably about a year long to do that type of construction. So there was a tremendous savings of time here too. These are some more close-ups of typical construction. Again, our project was mainly widening. So if you look here, I'll bring my cursor up and look on the inboard side of this slide on the right. You can see the existing embankment, and the EPS is being brought up and benched into that existing embankment. And then the outside part of the embankment, which is vertical, the EPS is obviously placed vertical to stay within the limits of the right-of-way. So we were able to do this construction and stay within right-of-way. And then on the left-hand slide where I've moved my cursor area, you see the EPS here, a reinforced concrete load distribution slab placed on top to protect the EPS from traffic loadings, and then granular base materials were placed on top of that, and then the concrete pavement. And then the face of the EPS was protected by precast tilled-up concrete panels. So that is very typical construction that we were doing in those days. Here's another interesting slide of a very beautiful EPS embankment done for the SR 519 project in Seattle, a curved on-ramp on compressible ground, again having to be done relatively quickly on soft soil. So this is again showing that you can certainly create some fairly elegant embankment, with the block and block placement. Another thing I'd like to point out is after the use of EPS on the for roadway construction, the Utah Transit Authority was reconstructing later on some of its light rail lines in the Salt Lake Valley, and expanded polystyrene was used quite extensively in some of those areas too. What I'm showing here is the light rail to West Valley line from Salt Lake City out towards the west. This also goes towards the airport. And you can see here on the left an EPS embankment being built as lightweight embankment against a bridge abutment, which is pile supported. And then on the right is the same embankment, but you're seeing it more in profile view. And you can see the load distribution slabs being poured on top of the EPS. And then down here in the lower right, you can see the reinforcement coming up for one of the catenary poles. This is an electrified system, and so the load distribution slab, which protects the EPS, and the foundation of the catenary pole were integrated in this case as part of this. And then later on, this gap between these flat slabs was also, concrete was poured in there in reinforcement manner. But we found over the years it's easier to pour these slabs horizontally and then slope the EPS embankment in the gaps between the slabs, and then come later on and fill that in with concrete. It's just a more convenient way of construction. Another thing I'd like to point out is everything I've shown you thus far has been where bridges have been supported on deep foundation systems. The Norwegians, though, have some very problematic soils. These are quick clays that obviously, if you disturb them, can liquefy and flow. And so in some cases, they cannot really drive conventional piling and do some of the ground improvement techniques that would normally do, maybe to improve the ground. So they came up with the idea to maybe support the bridge itself directly on the polystyrene on a spread footing instead of deep foundations. And that's the construction I'm showing you here in the upper left. You can see a forming work for the spread footing going in place on a sloped expanded polystyrene embankment. And then later on, a steel truss bridge, single lane, was placed and supported on this. This was a temporary bypass ramp for the intersection, but it worked so well that they left it in service for 17 years. So I don't think that really classifies as temporary, but it is very interesting construction. They have repeated this for 2 other bridges, and one they have also remediated a reinforced concrete bridge that was settling, and they've shored up and replaced one of the abutment areas in the embankment with polystyrene and supported the bridge on polystyrene. And they've done several cases of pedestrian bridges too, supported on polystyrene. So I would point out that if you have rapid construction of lightweight bridges, whether they be lightweight steel bridges like this or pedestrian bridges, expanded polystyrene becomes a very fast way of constructing these abutment areas without the need of deep foundations, and essentially not inducing any significant settlement. This slide shows more of a sloped application. This happens to be in Arizona. It was a widening project on a slope that was somewhat unstable. And also, I'll see if I can bring my arrow back up. If you look off to the left here, down off the base of this spill slope, you can see that this was sacred ground to the Hopi Indians, so there could not be any disturbance beyond this part of the project. So the polystyrene allowed 2 types of construction. First, a widening without inducing any significant loads on this area that could become potentially unstable, at least by the slope stability analysis, and also allowed a vertical embankment to be constructed to stay within the limits of the right-of-way. Another thing we've been using polystyrene a lot for is to protect buried objects, particularly pipes and culverts. There's different ways you can do this. This slide shows maybe 4 kind of concepts. So in the upper left-hand corner on slide A, you can see a buried pipe, and you could build a lightweight cover system over this buried pipe system using EPS in kind of a inverted trapezoidal configuration. And you can make the loadings on that pipe very inconsequential in terms of, dead vertical loads, and somewhat dead, and also the horizontal loads are greatly decreased too. Of course, if you're doing a trapezoidal configuration like this takes a lot of right-of-way, and so it may not be the preferred way when you have tight right-of-way constraints. Another idea is to put EPS as just a block of EPS over the top of the culvert. In this case, you don't get all the benefits you'd get on the left, but you can still get maybe a 30 to 50% reduction in the vertical earth pressures by creating what we call a compressible inclusion. The EPS in this case compresses with the embankment that's placed on top, or the fill that's placed on top, and helps induce the arching effect within the fill, which then can reduce the loads on the pipe. So this is a very complex pipe EPS soil interaction, but it's been proven both numerically and by measurement that this concept works. And there are several people who have done research and given some guidance on how to design these systems. Another one that I want to show later on is in slide C. We had a particular case where a high-strength steel pipeline had to cross a fault in Salt Lake Valley, and we designed the pipeline on the downside part of the fault to literally pop upward and not be restricted by the earth. And we used a slot trench idea with EPS blocks as a configuration placed on top of the EPS to allow the pipe to move freely upward when the fault dropped downward. Of course, this all occurs in milliseconds, so the rapidity of this is one of the design considerations, but both in numerical modeling and testing of some pipe pullout tests where we built this system in situ and used a crane to pull pipe up, we proved relatively well that at least the bending stresses in the pipe were sufficiently reduced so that the pipe would survive the fault offset without rupture. Another idea that came to me from an applied problem where a sewer was settling, the line was quite fragile and they wanted to reduce the loads on the pipe. It was in an area where the ground was settling. So we built kind of a slot trench again over the pipe. The pipe was repaired, and then to keep the pipe invert and the flow, it's a gravity flow system, so to keep the flow going through the pipe properly, we put a concrete slab and hung down a hanger to support the pipe, and this could be adjusted with time through an access. And so this was allowed for continued settlement but no damage to the pipe, and it worked quite well. Okay, so it's just some construction slides. This is kind of an inverted trapezoid idea. This is a widening for the commuter rail system in the Salt Lake Valley. You see in the upper left-hand slide the culvert that's being extended. In the widened area, you see the beginnings of the EPS block being placed in an inverted trapezoid. On the upper right, you see the progression of the EPS embankment, the final configuration of the EPS embankment. Notice the geomembrane is missing in this final configuration, and I'll talk about that just a little bit later. And then finally, the final configuration with earth topsoil covering and protecting the EPS system and the commuter rail deflecting, the commuter rail driving over this EPS embankment. We've used accelerometers to measure the dynamic deflections of these EPS embankment systems, and we believe that the deflections are somewhere around maybe 6 millimeters maximum, which is not of any consequence, at least to this commuter rail system, which through this area is running about 70 miles per hour. Okay, I am showing here in this slide the Wasatch Fault in the southern part of the Salt Lake Valley. You can kind of see the fault trace here in a series of offsets from multiple events that have occurred on this fault. It tends to rupture about on average every 1,000 years. And the offset due to any individual event is 2 to 3 meters of offset, which is damaging to many pipelines that would try to cross this area. So I was approached by the local gas utility, Questar, to see if there was some way that we could reduce, well, let me put it this way, how we could make the pipe cross this fault and survive the offset without breaking the pipe. This is a natural gas line, high strength steel, and if it were ruptured, it usually can turn into a very large conflagration and be a very safety hazard during the earthquake. So it's a challenging thing to try to do. So we went through, again, numerical modeling, laboratory testing, testing within the field. What I'm showing here is the final configuration we agreed upon. As you can see, the high strength steel pipe, ductile pipe being placed downward. It was then embedded with about a foot of sand for cathodic protection of the pipe. Then on top of that, 2 to 3 blocks of EPS were placed to bring the pipe back up to roadway configuration. You can see a geomembrane being placed on top of that material, both to protect the geofoam and also reduce some of the side friction along the EPS as it tries to pop upward during the earthquake. And then we're pouring a small reinforced concrete slab on top of the EPS to protect it somewhat from any traffic loading. So this is kind of what was constructed, and this has been done 4 or 5 different areas now within the Salt Lake Valley where pipelines are crossing fault systems. Okay, so those are some applications that I've shown. They're certainly not exhaustive. I could show you many more slides about different construction, but I think that gives you an idea of some of the main applications. I want to also talk a little bit about preparation. I'm going to focus more on the construction preparation than maybe some of the other things that we would do more from the laboratory testing side, which is on the left. But on the right-hand side, I'm going to talk about bedding material compaction and also talk about chemical attack and potentially issues of moisture absorption and buoyancy. So when we place EPS block, we have to be careful how we place it, not to create continuous vertical joints. So quite often we alternate the direction of block placement each layer. So in this slide, you can see the base of layers going from left to right, and then the next layer is going in and out, and the next layer is left to right, and so on and so forth. So we alternate the directions. We also stagger the vertical joints so we don't create continuous vertical seams through the EPS. I forgot to mention too, quite often before we place this, particularly on really soft ground, we would put a non-woven geotextile fabric down as a separation layer between the maybe more clay and wet soils, and then on top of that separation layer is some bedding sand that's placed to help as a under drain underneath the EPS, but also provide a leveling platform. Okay. So let's talk about chemical attack. Expanded polystyrene is susceptible to degradation when exposed to petroleum products. So what we now do quite often is there's two methods of protecting from chemical attack. Well, before I talk about those methods, let me show you the types of things that can attack the EPS. Is gasoline, obviously, petroleum, other petroleum-based products and organic fuels. And there's different strategies, concrete encapsulation, which I'll somewhat show you. That was the predominant way we did it on I-15. Certainly, geomembranes can also perform that same function, particularly when you have sloping side slopes. That's a good idea. And then also for vertical fascia walls, you can use panels to protect the EPS from spills. I would point out that anytime you get a petroleum product spilled in an embankment area in soil, you've created a potential hazardous waste. So you have to generally excavate that soil in a timely manner. Depending on how much petroleum product is in the soil, you may have to also put it in a hazardous waste landfill. So there's some testing required to see what needs to be done with it. There's different ways of treating petroleum contaminated soils. But if you do damage the EPS areas from a petroleum spill, which has not happened yet, by the way, worldwide that I'm aware of, but if you did, you could come in and replace any damaged block at that time from petroleum contamination. So there are some questions about what is the preferred way to do this, whether you use geomembranes or concrete low distribution slabs. We put this question to the Federal Highways Administration. This was I'm showing a little bit of a memo between Nico Suttmuller and Silas Nichols, and basically they chose to not say there's any position by the FHWA. Either a geomembrane could be used as a protection barrier against petroleum spill or a concrete low distribution slab. So here's kind of a view of both. On the left, you see the concrete slab being poured, reinforced, and on the right, you see a sloped embankment with a geomembrane. I would say that probably the left-hand side is more commonly done in urban construction, where you're often doing vertical embankments and protecting the EPS against heavy truck traffic, such as semis, whereas the right is maybe a little bit more common in rural areas where you may be using sloped embankments because you don't have as severe of right-of-way constraints. But either way will work. There are geomembranes, several geomembranes are compatible with the EPS, polypropylene, polyethylene, CSPE, and ethylene interpolymer alloys can all work. But I would point out that in terms of the petroleum, these have various degrees of resistance and protection. So I think the best thing is if you're exploring these different membranes for protection, to consult with the producer and their testing results about their ability to protect EPS from petroleum products. So I'm going, this rather lengthy slide, I think I'll just go and show you what we had to do for the I-15 project. This is just a typical drawing, and you see the EPS block here. On top of it, a reinforced concrete slab. On the side slopes and tucked in underneath the reinforced concrete slab was a geomembrane. I'll show you the 3-component membrane in just a minute. That was brought into the side slopes. This would be the existing fill of the existing side slope. Then the base material here, an additional concrete pavement slab on top, unreinforced concrete pavement slab, then the tilt-up panel wall and a connection here. So that was the encapsulation system that we used on the I-15 reconstruction. The tripolymer geomembrane, as called out in the specification back in 1996, was a polyvinyl chloride geomembrane. Well, it was component. In the middle is ethylene interpolymer alloy and then polyurethane. The maximum thickness of all 3 components was 9 millimeters. There's also considerations too about your storm drain systems, placing them within the EPS. We still recommend you can put a geomembrane in to protect against any petroleum products that might get in the storm drain system and possibly leak through it into the polystyrene. In some cases, we also would put a low strength concrete fill as an infill material within the embankment, and that worked quite well. Moisture absorption and buoyancy, let's talk just briefly about those. This probably has more to do with landscaping applications where you have the possible infiltration of rainwater down through the fill and possibly into the EPS. So obviously, if you have a large storm event, you could get some water coming into the system, and there's a couple ways of dealing with this. I think the most common way is to put the geomembrane on top and then possibly put a French drain system on top of the geomembrane to collect any water and carry it out to a collection system. I have seen some cases though where the geomembrane on the top has been omitted and it's been placed on the bottom as a waterproofing, and then the French drain collection system is placed at the bottom. I think both are acceptable, but they are, things that you need to talk about with the landscape architect as you plan on doing these type of things. Just some construction pictures, just briefly showing EPS used. Here's a geomembrane on top with the EPS block being placed, and then landscaping. This is lightweight fill materials on top of a parking structure, and you've got a green area or landscaped area. So the EPS is used as lightweight fill to come up to a certain grade without causing any significant loading on the top of the parking structure. Here's another case near the state capitol, very similar type of construction. A geomembrane is placed down as a waterproofing. In this case, there had been a recent storm, so you can see a little bit of water that's ponded here. That would have to be pumped away. And then the EPS being placed on top of the geomembrane, and then landscaping done on top of that. Roofing is being done a lot here in Asia and in many places where the EPS in conjunction with the geomembrane being used. This is the conference center in Salt Lake, downtown Salt Lake, where the landscape green roof has substantial amounts of polystyrene placed on top of the geomembranes. One word of caution before I end here is when we're placing geomembranes in high seismic areas, you have to worry a little bit about what is the sliding resistance between the geomembrane and the polystyrene. For some projects, this can be quite low, And if you have high levels of ground acceleration, you have the potential of interlayer sliding, mainly between the geomembrane sliding on top of the geofoam. So be careful. This was placed for the commuter rail system that I showed earlier in my presentation, and you see the geomembrane being placed, but when the design engineer further considered the seismic loadings, it was determined they should maybe remove the geomembrane. So the final configuration, there was no geomembrane. So this is really probably, in my view, something that if you have moderate to high levels of ground acceleration, you need to pay attention to this particular issue. Okay, I think I've finished pretty much. I want to point out to you that a lot of the applications are available to you. This is a pamphlet that Tim spearheaded some years ago. Tim was involved, myself and Dave Arliano. It's a little bit hard to chase down, but the link that I provided here in the presentation, you can find this and other information about expanded polystyrene, and it's quite a good pamphlet to show you, I think, the different applications and typical conceptual drawings of how you put these systems together. And so I will finish and turn it over, I guess, back to the moderator, Tim, for any questions.
Great, Steve. Thanks very much. We have, well, there's a lot of questions, right? 4 questions right off the bat. First is related to the I-15 project. How were the tilt-up concrete facing panels anchored at the top? And there's some other questions, but why don't you answer that first?
Okay, let's see if I can quickly go back to that detail.
Okay, while you go back, were they connected to the load distribution slab?
Yes, there was, but there was a problem with that initial connection. Initially, it was connected with rebar and somewhat rigidly. And as you place the materials on top of the expanded polystyrene, namely the low distribution slab, the base, and the concrete slab, that compressed the EPS slightly and caused a little bit of damage to the connection. So you have to have a little bit more of a flexible connection. I think I've seen some pin connection ideas, and I've also seen one where you have kind of a slot connection. But yes, just pay attention to it. But yeah, the short answer is it was connected with the low distribution slab.
Okay, let's see. Dead man through anchorage or anchorage.
So there was a connection. It's not shown in this detail, but there's a connection right here.
Okay, moving forward, do you think that connection is required? You mentioned a flexible connection, so it sounds like at least some kind of connection should be included.
Yeah, you can either do it with a structural detail to realize that there is going to be some dead load compression of the EPS as you put weight on top of it. Another way that I saw the contractor do was they would slope the embankment back in this area, leave the connection exposed, not make the final connection until final load was in place, and then make the connection. That worked also.
Okay. All right. Good question, Tom. Next question. What elevation step heights were used between the horizontal LDS areas on the Utah and Washington projects?
So are we asking what are the thicknesses of the slabs themselves?
What elevation step heights were used between the horizontal load distribution, I guess that's load distribution slab, on the Utah and Washington projects? Or Matt, if you want to refine
that. On that, but I think they were 4 to 1s, 4 horizontal to 1 vertical were the steps.
4 to 1?
And yeah, and on the Washington project, I'm going to have to defer a little bit because I was involved in the initial design, but I don't know the final configuration. But I think, 4 horizontal to 1 vertical, the concrete will still hold without much slumping there in those stepped areas where you're pouring in that concrete in on kind of that ramped area.
Right. Okay. Next question. Has geofoam been used anywhere around the world with buried high pressure natural gas pipelines, which I think you covered in Salt Lake City? It was mentioned as a solution, but later people objected. So maybe talk about high pressure natural gas pipelines.
Okay. So this is a construction photo, and the idea here is that when the design engineers looked at In a normal faulting system, and I have to make sure everybody understands this is a normal fault, so we're not talking about strike slip. So the predominant movement on this fault is vertical. On the down drop side of the fault, the upside of the fault basically stays stationary, and really it's the down drop side that's moving downward relatively. On the down drop side of the fault, if you buried the pipe, this is in urban construction where the pipe's maybe 6 to 8 feet to 10 feet deep. If you put that amount of fill on top of it and you expose the pipe to that rapid down drop, as the pipe tries to uplift upward through the down dropped cover system, if you're using normal backfill materials, there was still a chance of rupture. So the idea is the EPS essentially acts like a cork. It's lightweight. It's in the slot trench, and so as the pipe tries to move upward, it just compresses and pops that EPS upward. And the numerical modeling and testing we did, I think we concluded over what they were planning to do, the bending stresses in pipe were reduced by a factor of 4. And so the pipe engineers felt that their high strength steel pipeline was strong enough to survive that event with the EPS cover system. So they were relatively happy. So, I think the key here is that this pipe is quite ductile. And so for high strength ductile pipe, I think the concept worked pretty well. I would put some caveats on this for, reinforced concrete pipe or other types of pipe systems.
Okay. And Josh Butler mentions he just used Geofoam for a large 12-meter embankment over a LNG pipeline in Portland. So
yeah, and that would be probably more maybe I think what you would see here in slide A, that type of configuration.
Yeah. Yep.
So that configuration, particularly in slide A, you can reduce the loads on the pipe significantly, but because you're essentially creating an internal stable backfill here and not putting a lot of load here, this should be stable here. You can decrease the vertical loads and the horizontal loads quite significantly, but it takes more construction space.
Yep. Yep. And Josh agreed on that. Okay. Next question. Does Geofoam have any environmental concerns? That's the question. I'm not sure which environmental concern.
Well, there is some off-gassing of pentane. That's why maturation and curing the block is important, so that the off-gassing occurs before you significant off-gassing of pentane before you place it underground. I don't think it's really a big issue, but the Japanese sometimes were placing blocks soon after they had molded them and they were getting some pentane that was coming up. Also, in the United States, we standardly put a fire inhibitor in the expanded polystyrene so that it's self-extinguishing. And I think in fisheries and areas where you might have potential placement near streams, the Europeans are becoming a little bit nervous about that fire inhibitor. So the polystyrene now being placed in Europe does not have the fire inhibitor. So I think that's the major two concerns. Other than that, it's fairly inert with its environment, both chemically and physically.
Okay, thank you. Next question. Is there a DOT standard for geomembranes covering geofoam in highway application? This standard was originally developed by Caltrans and was the spec used for the I-15 project.
That'll have to, states have many different specifications on geofoam and they're not necessarily standardized. Ours was a special provision within the contract that preceded any work done by Caltrans, but it's quite dated. When I mean ours, the one used by the Utah DOT. So I think it's going to vary widely amongst the various states. What you're going to get is terms of the calling out of a specification and what are the types of geomembranes allowed.
Okay.
It's not standardized.
Okay, so there's not a US DOT standard available.
Not that I'm aware of, and I don't know, with what you and Dave wrote some time ago for NCHRP 529, you may have called out something there, but my interaction with the various states is they're either adopting standards from other states or developing their own. But no, there's nothing coming directly from federal highways saying, you know, this is how it should be.
Yeah, I don't remember. I have to go back to that report. Let me go back to an early question that was, what elevation steps were used between the horizontal LDS areas on the Utah and Washington project? Matt clarified his question. My question was about the step heights between the flat horizontal areas for Utah and Washington project. So maybe that's the block height.
Yeah, okay. So let me see if I can do this by eye. Yeah, I don't think they're a full height block. Close to it though. So probably about 3 feet.
I'm sorry, Steve, 3 feet?
On this slide I'm showing, which is the Utah Transit line, I'm kind of bringing my arrow in the stepped area, and that's probably about 3 feet.
3 feet.
And that's not obviously on a 4-to-1. That's steeper than a 4-to-1. That's probably maybe a 2-to-1.
Okay, so Matt, 3 feet to a meter in step height and slope, maybe
Yeah,
4-to-1 to 2-to-1.
yeah. This is probably not quite a meter here. You can see it down here too, and this is probably about a 2-to-1. That's what I'd guess.
2-to-1, yeah. Okay. Next question.
But if Matt would, you know, send me an email, I can find UTA's typical drawings. I think I have those.
Yeah, that's a good point. And Steve's email address will be on our last slide, and feel free to send him some additional questions. Having projects in Africa, is it easy to transport this material, and does it require skilled labor to install?
It's easily transportable, but it may be economically unfeasible to transport geofoam over very large distances. You know, I think in the United States, there are block molders that maybe have transported EPS up to 1,000 miles. But, you know, trucking costs, it's lightweight, so you can use it. You don't have to even have full-size semis sometimes to transport the materials, but you're paying extra fuel costs. So, you know, it becomes less competitive when you don't have a block molder that's maybe in the same country or nearby.
Right.
That can be a problem. The other question was what? There was a second part to that.
And does it require skilled labor to install?
Generally not. You need a supervisor or foreman that's done this before, but quite often with a technical oversight and a foreman that's been involved in block placement, he can train the local contracting crews to do this. That's usually the way it's done.
Yep. Okay, another question. I assume EPS has limited use below groundwater due to buoyancy. Do you have any experience or use of EPS below groundwater?
No. Construction becomes more problematic. We've placed EPS close to groundwater, but always, at least the projects I've been involved in, we were above groundwater. The other consideration I didn't talk too much about is buoyancy, that if you have EPS embankment with cover on top of it and you have a design flood that can inundate the roadway completely, you have to make sure you have enough weight on top so that buoyancy doesn't become an issue. And that's a design consideration, and we've done that many times and tested that design. And in some extreme cases, you could put a fabric or a membrane on top and use an anchored system. But generally below groundwater, in my view, is problematic. It's not impossible, but it becomes more problematic.
Right. Yeah, place it above it, and like you said, design for the flood, and there's a design procedure in the NCHRP manual to make sure you have enough total stress on top.
Correct.
Such that you don't float the block. Okay.
Correct.
Let's see. Steve, I think those are most of the questions. Maybe let me wrap up with a couple quick questions. For example, in a short, brief statement, any emerging uses of geomembranes or other geosynthetics for geofoam applications?
Well, certainly pay attention to what's going on in the landscaping world. for my conversations with many of the block molders in the United States, it's beginning to be maybe as much as 30 to 50% of their business. And quite often you're going to see many geotextiles incorporated in those green roof systems. So I think, there's still a lot to do there. In my view, one unanswered question we have fundamentally is, if we allow EPS to percolate down through the block and catch it with an underdrain, what is the potential infiltration rates down through the block itself? We don't really know. So I've been in some projects where, there was thought, well, let's catch the water from a green roof, catch it down below in an underdrain. But then the question was, what is the rates of water coming down through that from the design storm event? We didn't really know that, so they said, well, maybe we'll just put a geomembrane on top and capture on top with a French drain system. So I think as we start integrating geofoam with other types of barriers, membranes, and systems like that, then that's going to be really important.
Yep.
We're using polystyrene also against buildings to reduce earth pressures and seismic earth pressures, and that's very much an emerging market, and often those are incorporated with geomembranes and waterproofing that's used against the building. And the thing we're thinking about here in Korea is also building solar arrays where polystyrene, maybe reinforced concrete, and geomembranes all have a role in creating floating platforms for the solar panels. So yeah, there's many things that are still going on. And of course, I showed the bridge support 2 systems, and those are evolving too. So, research has not stopped. It's just that we're expanding some of the original concepts and verifying and developing, more and better design guidance.
Okay, we're right about noon, so let me go to the end of the slides. And before we end, I want to encourage everyone to visit the FGI and IGS North America websites shown on the screen. And let's see, Steve, maybe you can page down to...
Let's see if I can do that. Right, let's see, just a minute. It's the last slide?
Yeah, I think it should be the last slide. There's some contact information for...
This one?
Let's try... Nope, go one before that. One before that. Yep. Okay, so here's contact information not only for Professor Bartlett, but also the Fabricated Geomembrane Institute and the North American chapter of the IGS. They're shown on the screen, and hopefully you will visit these websites, learn more about these organizations, and consider joining and becoming involved in these geosynthetic industry groups. Okay, Steve, if you go to the next slide.
This one?
Our next webinar will be on June 25th, Geosynthetics for Coal Combustion Residual Applications. And then the next slide gives the upcoming webinars after June. Oh, sorry. Nope, this is our website, the FGI website. Okay, so Steve, thanks so much for joining us from Incheon, Korea. And thank you for everyone that attended today's presentation.
Thank you for the thank you for the chance, Tim.
Thank you, Steve.